This video is on section 5.2 notes, the normal distribution. So the normal curve or normal distribution looks like this, and it's a distribution. And when I talk about distribution, I'm saying if we were to take data and put data, it's a distribution of data that is a bell-shaped curve. This is what they mean when they say bell-shaped, with most of the data points near the mean in the middle and fewer data points away from the mean. So most of the data that you have is repeated data, or very, very similar decimals that are close to the data. All of the data would be right here, and then as you get further away, that data is more spread out or is not used as much. So here are some properties of a normal distribution. A normal curve is bell-shaped. This is what they mean by bell-shaped. The curve is symmetric with respect to the mean. So the mean is right here in the middle, where the curve reaches its highest point. The mean, median, and mode of the distribution are all the same. So the mean is that average you calculate when you do the sum divided by the number of data points that you have. The median is the middle value, and so they're saying the middle value happens to be the same as the mean. And then the mode is the value that is repeated the most often, and that also happens to be the same as the mean. So in a normal distribution, all three of those are the same value. The total area under the curve is 1. So this whole area in here is calculated as 1, and we'll get into that a little bit more throughout the notes. It says roughly 68% of the data values are within 1 standard deviation of the mean. So if you have the mean plus a standard deviation and minus a standard deviation, that's going to include 68% of the data. 95% of the data is within 2 standard deviations. So if you start at the mean and add 2 standard deviations and subtract 2 standard deviations, that's going to be a range of values that's going to include 95% of the data. And then if you go 3 standard deviations away, that's going to include 99.7% of the data values. So let's go ahead and do an example using a normal distribution. This problem says, suppose that the distribution of scores of 1,000 students who take a standardized intelligence test is a normal distribution. If the distribution's mean is 450 and its standard deviation is 25, then how many scores are expected to fall between 425 and 475, and how many scores are above 500? So the first thing I'm going to do is take the mean and label that right in the middle, so 450, and then the standard deviation is a score of is 25 points above and below that. So I'm going to add 25, 475, add another 25, 500, add another 25, 525. And then I'm going to do the same thing, but I'm going to go backwards. 425, 400, 375. So the first question is how many scores fall between 425 and 475? And 425 to 475 is down 1 standard deviation and up 1 standard deviation, and that is 68%. So 68% of the scores are up a standard deviation and down a standard deviation. For the other one, we're looking at how many of the scores are above 500. That's all these over here. And for this, we have to do some math. So I'm going to go back up here. I'm going to do the math on this normal distribution. So this will be kind of like a formula sheet that you can use when you look at other problems. So if this right here, 1 standard deviation below the mean and 1 standard deviation above the mean is 68%, that means that half of that 68% is below and half of that 68% is above. So this would be 34% and 34%. And I'm going to go ahead and write those as decimals. 0.34 and 0.34. I'm writing these as decimals. And I'm doing that, I guess I'll write them as both actually, percentages and decimals. I'm going to write them as decimals so you can see why people say the area under the curve is 1. Okay, so 34%, 34%. Then if we have 2 standard deviations is 95%, then I would take 95% and subtract that 68%, and that gives me 27% that I can split between right here and right here. So I'm going to divide that in half. I'm going to split it, and that's 13.5% in each of those spaces. 13.5%, 13.5%, which as a decimal is 0.135. 0.135, 0.135. Okay. Then 99.7% of the data is between 3 standard deviations below the mean and 3 standard deviations above the mean. So I'm going to say 99.7 minus 95. So that means 4.7% is right here and right here. And I'm going to split that in half. And so that's 2.35%. 2.35% right here and 2.35% right here. And so for the decimal that's in this little area right here, that would be 0.0235. I would have to take that decimal and move it 2 places to the left to write this as a decimal number. Okay, and then anything that is beyond 3 standard deviations, maybe 4 standard deviations, 5 standard deviations, 6 standard deviations, anything that's extremely low or extremely high, we call those data points outliers, and they're going to be anything that's outside of 99.7% of the data. So 100% of the data minus 99.7% of the data, this 0.3% is going to make up all of those extra outliers. And I'm going to divide it in half and do half above and half below. So we have 0.15% above and 0.15% below. And if I think of, if this little bell curve, if it kept going and there's just a very small area in here, then I could do 0.0015 for the area 0.0015. And if I was to add up all of these areas, a 0.34 area, 0.135 area, 0.0235, and 0.0015, they're all going to add up to 1. So it adds up to 1. So that's where they say the total area under the bell curve is 1, is it's because it's all of these areas that represent the percent chance you have of the data falling in those values, or the percentage of your data that's in those values. So if we look back at this example problem said we have a data value that is 2 standard deviations above the mean, and they want to know what percentage of the data is more than 2 standard deviations above the mean. So what percentage of the data is above 500? And that would be 2.35% and 0.15%. So 2.35% and 0.15%. And that's 2.5% of the data. So you don't have to do this math again. You can just refer back to your notes, and these decimals are going to say the same every time. You don't have to use these ones. This was just so that we could see that it added up to 1. But the percentages that we wrote, the 34% and 13.5%, those will be good to have in your notes. so that you can do other example problems or other homework problems on MyMathLab that ask questions like this. Okay, let's go ahead and look at the next problem. The next problem is talking about z-scores, and z-scores are just the number of standard deviations that a data value is from the mean. So if we look back on the previous page, a score of 450 has a z-score of 0. That's exactly the mean. A score of 475 has a z-score of 1. A score of 500 has a z-score of 2. So if we had two people and they were comparing test scores and one person said they had a z-score of 2.5 and someone else said they had a z-score of 1, the person with the 2.5 is like, haha, I beat you. My z-score's higher. I did way better than average than you did. If somebody says I have a z-score of -3 and somebody else had a z-score of 1/2, the person with a z-score of 1/2 should be more excited because their score is higher than the person who had a z-score of -3. So it's a way for us to compare how well someone did if they compare their score to the average. Okay, so let's look at the z-score for these different values. So it says to find the proportion of data underneath the curve that lies in the following region for a standard normal distribution. So here is a table, and this is out of your textbook, but I went ahead and just copied the page and made it so you could print it just directly from this. And the way that this works is you find the z-score, you look along the side for the whole number and the first decimal place, and then you look along this column right here, or this row right here, for the second decimal place. And it gives you the area between the middle, between the mean and the z-score. So here in that area is the probability or the percent chance that the data value is between those z-scores. So, or the percentage of the data that falls between those z-scores. So if we are looking for the z-score or the percent of the data that's between a z-score of 0 and a z-score of 1.3, then I would look here and I would look for 1.3, and it's going to be 1.30 because there is no other decimal place. This would be 1.31, 1.32, 1.33, 1.34, but they just said 1.3. So I'm going to use this one. And so the z-score gives us a percentage of a probability of 0.4032. So 0.4032. So for whatever data set this is describing, 0.4032 is the proportion of the data that falls between the mean and a z-score of 1.3. That's how much of the data falls there. So if you had a data value, this is the probability that your data value is between those two z-scores. All right, here it says find the area under the curve between 1.5 and 2.1. So we're going to do two calculations. Our table can give us the area from 0 to 1.5. And it can give us the area from 0 to 2.1, but it can't give us the area in between them. So we're going to have to do some calculations to find the area that's in between these two. And you can see right here, this is the area that's in between 1.5 and 2.1, and this is the area they want you to find. So we can go ahead and find these two separate areas. The area between 0 and 1.5 is this, 0.4332. 0.4332. And then 2.1 is 0.4821. 0.4821. So the area between 1.5 and 2.1 is going to be this entire area from 0 to 2.1, subtract off this smaller area. So if 1.5 is right here, then 2.1 is a little bit further. It's over here. And we're looking for this little sliver of an area between them. So we're just going to do 0.4821 minus 0.4332. And when we subtract these two, it's going to give us the area that's in between them. .0489. So the area between them is 0.0489. All right, here they've made things a little bit more complicated, and they said, okay, we have a negative z-score over here, negative 1.83 and positive 1.83, and they want you to find the area between these two. Now the table that we have, it doesn't give us any of the negative z-scores. You'll notice that all of these are positive over here. So I can't find this area on the table. I can only find the area on the right. I can only go from 0 to 1.83. So that's what I'm going to do first. I'm going to go from 0 to 1.83. Here's 1.8. And then I have to go to 1.83, which is right here. And I know that because here's the 3. So this is 1.80, 1.81, 1.82, 1.83. So it's 0.4664. This is 0.4664. And then since these are symmetric, that means that if this value is 0.4664, then this one is as well, 0.4664. So to find the area under the curve between negative 1.83 and positive 1.83, I just need to take these two areas and add them together. And I get 0.9328. 0.9328 is the area under the curve between 1.83 and positive 1.83. And the reason that we are interested in the area under the curve, again, is because it describes the probability that the data that you're working with is between those values. So whatever data value has a z-score of negative 1.83 and whatever data value has a z-score of positive 1.83, I could figure out those data values, and then I could say for my whole set of data, the probability that the data is going to be between those two values is a probability of 0.93. Or I could phrase it as 93% of the data lies between those two values. So that's why this is a significant thing for us to learn about. That's why we care about z-scores. All right, now of course it's going to be important for us to be able to take a problem where we are given data and take a piece of data and figure out what the z-score is. So that's what we're going to do next. We're going to use this formula, and the formula is that the z-score is the data value minus the mean divided by the standard deviation. So this is the data value minus the mean divided by the standard deviation. And you're seeing these Greek letters. This is the Greek letter mu. This is the Greek letter sigma. They're showing you these Greek letters because in statistics, they use a lot of Greek letters to mean different things. So they gave you this formula in the Greek letters, but this is what the formula really means. Okay, so here it says, in an effort to combat dog obesity, the Association for Pet Obesity Prevention has weighed a group of Basenjis, I think is how you say that. They're African barkless dogs, and found the distribution of their weight to be normally distributed, so it uses this bell shape, with a mean of 20 pounds and a standard deviation of 3 pounds. So I'm going to go ahead and fill in this distribution, not because I need it for the problem, but just because I like to use it to see what I am working with, to see what my data should look like. It says, find the corresponding Z-score for a dog in this group weighing 25 pounds and weighing 16 pounds. So I know that a dog that weighs 25 pounds is going to have a Z-score that is close to 2, but a little bit less than 2, because it's a little bit less than 2 standard deviations. I know that a dog that weighs 16 pounds is going to be a little bit, it's going to be close to -1, because it's almost 1 standard deviation below the mean. So it's going to be close to -1, but not quite to -1. Okay, so I'm going to go ahead and calculate my Z-score. I'm going to say the data value minus the mean divided by the standard deviation, and the data value minus the mean divided by the standard deviation. Okay, so to type these into my calculator, I can type them in like a fraction if I use the alpha button and then this button and use the first option. So 25 minus 20 divided by 3. I get 5 over 3. I'm going to go ahead and turn that into a decimal. And with Z-scores, we like to write 2 decimal places. So I'm going to write 1.6, and then with the other 6, I'm going to convert that into a 7, because with 6s, we should round up. So this is 1.67. And if you don't like typing it in as a fraction, you could just do 25 minus 20, and then divide by 3. For the other one, I'll do 16 minus 20 and then divide by 3, and I get -1.33. For this one, I don't have to round up because the 3's are followed by 3's, and those mean to keep the number the same. So between these two numbers, we've got one that is below the average, one that is below the mean, and one that is above the mean. This one is a little bit more extreme because it's further from the mean. 6.7 is further from the mean than 3.3, but they are, both less than 2 away from the mean, so they're both within typical values. All right. The next problem says, suppose that to qualify for a management training program offered by your employer, you must score in the top 10% of those employees who take a standardized test. Assume that the distribution of scores is normal and you receive a score of 72 on the test, which had a mean of 65 and a standard deviation of 4. What percent of those who took the test had a score below yours? So this problem is where we really start to see the benefit of Z-scores, because the Z-scores, when we look at that table, we can see what is the probability that someone would have received that Z-score. And here we need to know if this person is in the top 10%. We need to see what the probability is that everyone else they're being compared against also received the score they did. So that's why this Z-score is going to be really helpful for a problem like this. So they got a 72 on the test. We want to see what this person's Z-score is to see what the probability was that anybody got that score on the test and see if they're in the top or not. So we're going to do 72 minus the mean value, which is 65. divided by the standard deviation of 4. And we get a z-score of 1.75. So what we're going to do is we know that this right here is a z-score of 1.75, and we need to figure out what is the probability that all of the people who scored something on this test, what's the probability that their score fell between the mean and a score of 72? And that's what we're going to find by looking at the table. So what was the probability that their score was between the mean and 72? And it was 1.75. So here's 1.7. There's 0, 1, 2, 3, 4, 5. I can see that from up here. So 1.75 is 0.499. So the probability that they scored in here is 0.499. Nope, it was 0.4599. Yep, 4599. Okay, so we have to consider all the people who scored below the mean as well. So everyone who scored over here, this is half of the bell shape. So the probability that somebody scored down here is 50%, or 0.5. All right, so if somebody scored at 72, then this person is higher, the highest score out of all of these people. So 0.5 plus 0.4599. So if we add those together, this means that a score of 72 is in the 96th percentile. Only 4%, there's only 0.04 chance that somebody scored higher than a 72. There's only a 4% chance somebody scored higher. So this person with a score of 72 is in the 96th percentile, which means they are definitely in the top 10%, and so they definitely have the benefit of having a top score. And that means they qualify for a management training program. All right, we have just a couple of examples left. Here it says Ty Cobb hit a .420 in 1911. Ted Williams hit a .406 in 1941. In the 1910s, the mean batting average was .266 and the standard deviation was .0371. In the 1940s, the mean batting average was .267 and the standard deviation was .0326. Assume that the batting averages were normally distributed for both decades. Which batter was ranked higher in relationship to his contemporaries? So all you have to do in a situation like this, and I recognize here there's a ton of numbers, all you have to do is calculate each of their individual z-scores and see whose z-score is higher, who was better compared to the average of their day. So we have Ty Cobb. And to calculate his z-score, we're going to do his batting average, .420, minus the average of the day, which was .266, divided by the standard deviation, which is .0371. And then for Ted Williams, we're going to do his batting average, which was 0.406, minus the batting average of the day, which was 0.267, divided by the standard deviation, which was 0.0326. And then we're going to compare these, and whoever's z-score is higher was better in comparison to their peers. So 0.420 minus 0.266 divided by 0.0371. Z-score of 4.15. This is a very high Z-score. So we know that 95% of the data is between two standard deviations. So 95% of batters should be between a Z-score of -2 and +2. 99.7% of the data is between 3 standard deviations. So this means that he was like top. For his to be a z-score of 4.15 means that he was 4 standard deviations away from the mean, which is very, very high. So we'll check and see if Ted Williams beats him or not. So Ted Williams is also very, very high, and they're very close, but Ted Williams is a little bit better in comparison with his peers. So we'll say that which batter was ranked higher, it would be Ted Williams. But they were both very, very good. Those are very high standard deviations from the mean. All right, last example. Says, to increase sales, Samsung plans to offer a warranty on a new TV. In testing the TV, quality control engineers found that it has a mean time to failure of 3,000 hours with a standard deviation of 500 hours. Assume that the typical purchaser will use the TV for 6 hours per day. If the manufacturer does not want more than 5% to be returned as defective within the warranty period, how long should the warranty period be to guarantee this? So if we think about how we want this z-score to work, we're going to say for our z-score, we want some data value minus our mean divided by our standard deviation. We want this to spit out a z-score so that we have no more than 5% being returned. So we want to figure out the z-score so that we can figure out what the bottom 5% is. We want to figure out how many are failing and what this bottom 5% is. And we know that any that fail after that bottom 5% are fine. They'll be without that warranty period. They'll be past the warranty window. So we need to figure out what this z-score is that separates the bottom 5% from the top 95%. That's what we're going to be calculating. So I want this area right here to be 5%. I want the rest of this here to be 95%. Now, when I use the table doesn't measure from here up. It measures down the middle, right here. And it's not going to measure from the middle all the way to the right. It's going to measure from here to here. So we have to figure out what we're going to look for on this table to figure out what our z-score is. And what we're going to be looking for on this table has to say this is the bottom 5%. These are the ones that are defective, that are returned early within the warranty period. And then this is the 95% that would be without a warranty. So 95%, I'm going to say this is also 0.05. So that makes these two pieces 90%. And so that makes this 45% and this 45%. So I'm just breaking up each piece to see how big it is. Okay, and now what I want to do is, now that I know this is 45%, I'm going to look for a z-score that is the same as this 45%. So I'm going to look for a z-score that would give me that 45 probability. So in here, I'm looking for a probability of 0.45. So 0.44, it's right in between these two. This is a little bit under, this is a little bit over. So the z-score is 1.6. It's more than 1.64 and less than 1.65. So more than 1.64, less than 1.65. So the number that would be exactly in between those is 1.645. So 1.64, 1.65, the number that's exactly in between the two of those is 1.645. So this z-score is 1.645. This z-score is negative 1.645. So we want to figure out what data value is right here at a z-score of negative 1.645. Okay, so I'm going to go ahead and solve this, and I'm going to figure out what piece of data, how many hours has somebody been watching this television that would give us a z-score of negative 1.645. So this says divided by 100, x minus 3,000 divided by 500. I'm going to multiply 500 over to the other side. So times 500 times 500. X minus 3,000 equals negative 1.645 times 500, negative 822.5. I'm going to add 3,000. Okay, so somebody whose television is in the bottom 5%, as in these are the most defective televisions we have, is someone whose television fails to work after they've watched it for 2,177.5 hours. This is how many hours they've been watching that television. Now they told us that they're assuming that the typical purchaser watches television for 6 hours per day. So when you have a warranty on a television, they don't typically say that this TV is under warranty for a certain number of hours because everybody watches TV a different number of hours per day. So they don't say, keep track of how often you have your TV on and then tell us. They typically do warranties in terms of years: 1-year warranty, 2-year warranty, 3-year warranty. So what we're going to do is we're going to take this total number of hours and we're going to divide it by 6 hours per day and just see how many days it is and see if it's close to 1 year or if it's close to 2 years or if it's close to 6 months. We're just going to see what we get. So this many number of hours divided by 6 hours per day gives us 362.9 days. And 362.9 days is very close to 365 days. So for this, a 1-year warranty is going to make a lot of sense. If you have a 1-year warranty, then people whose TVs stop working after 2,177 hours, that's going to be the bottom 5%. They're going to say my TV is defective. They're going to ask for a new one. But anyone whose television stops working after 2,200 hours, 2,300 hours, 2,400 hours, those TVs should stop working after the 1-year warranty. And so they'd come in, they'd say, hey, my TV's defective, it's not working. And you'd say, sorry, it's been a year. We don't have to pay to replace it. You have to buy a new TV. Okay, so we calculated that using the Z-score to figure out what the bottom 5% was. And that way we're keeping control of our sales and making sure that we're not losing money because we're replacing too many TVs.